such a waste. You gotta reframe that. I know, I looked at it, I was like, it's so nice. Yeah, it's probably expensive too. Oh, this one wants stick to it from there, I swear. Oh my god. This was the greatest. I'm using it today. Just to make sure like I didn't miss anything. I know for next time it's spaced.
All right, so welcome back. I want to let you know that I don't have your whole test grades yet. Some of you haven't even taken the recitation portion of it. You're doing that today. But tests in general look very good so far from the portion that it was Scantron and 80% of your grade. So when I get the recitation results back from everybody, so I don't have actually anybody's recitation parts back yet. They're being passed around among the people that are grading them. When I get those back, I will put all the grades together, post them, and let you know that the grades are out. But so far, so good. I think the average score on the first portion, as if that were the whole test compared to the whole first test, was like 15% better than test one. So that's a good sign. I think you guys are getting it. Now, obviously, some of you can't have raised your grade 15%. So some raised your grade a lot, some just a little. I haven't had a chance to analyze yet because I don't actually have your full test grade. But just so you know, it's looking good so far. So what we're going to do today is get you ready for what we're doing next. We'll have an introduction to this so that if you want to over the break, you can go farther into Chapter 6, which is where we are now. But in any case, next week, full-fledged, we're going to jump into Chapter 6, which is not this. We started talking about getting accumulation from rates of change. That's what we just worked on for a month. But what we're going to do now is the other way around. So we actually did this a little bit already, very briefly. Chapter 4, in fact, was mainly about how to find rate of change from an accumulation function. We didn't necessarily talk about it in those terms at that point in time. But if you remember when we were working with Usain Bolt, we had his distance from the starting line measured in meters over a certain number of seconds. And we used GC to zoom in and calculate during small moments where it seemed he was going at approximately a constant rate, what those constant rates were. So that's kind of like the first step of what we need to do in order to reverse this whole process. So we started with that same sort of look at a few pieces at a time method when we were starting from a rate function and trying to figure out how can I use this for accumulation. And what we did before was we previously started with an exact rate of change function during Chapter 5. We decided that a good way to go about this was to pick certain number of points every so often, regularly spaced points on the exact rate of change function, meaning we're picking evenly spaced rate values through time or whatever the independent variable was, and using those each for a small amount of time, dx amount of time eventually, delta x to start with, to get an approximate accumulation function written in summation form, which took a while to set up. But if we can kind of generalize that process, then we took that, shrunk down our delta x length intervals until they're extremely small, so that we were essentially using all the values of the rate function. We ended up with a way to write exact accumulation, and we can just go from exact rate directly to accumulation without the middle steps, but knowing that that's why we're allowed to do that. That's what our open form notation, this exact accumulation written as an integral function, that's what it's expressing. It's expressing, summing up all the bits of change that are taken by using a rate in a small moment and multiplying by the length of that moment. So we've got our MDX sort of expression summed up from a to t, so, or a to x, whatever the letter might be. So we're going to go about doing this same process the other way around. It won't take nearly as long, as you'll see, because if you remember from when we were working from a rate function toward accumulation, we had to, if we wanted to actually know a total amount, like a total accumulation as opposed to just net, we actually needed extra information. And every time I need to measure accumulation, it depends on what the previous amount of accumulation was in order to extend this amount of net change. On the other hand, if all I'm looking for is a rate out of this, you can maybe think about this. Knowing the rate from one section doesn't help me find the rate for the next section. The old accumulation function helps me find that new rate, but the rates are actually needing less information than accumulation. I'm taking a part of the information that's there. It's like looking at a whole line and I just ask you what m is. It requires less information than mx plus b. So we are going to be going through a simpler process, but there's some tricky bits to making this work the way that we want it to. Specifically, we would really like to have a continuous function at the end. And if you can imagine, starting from an exact accumulation function, I can maybe imagine making a piecewise linear accumulation function that approximates that, right? Thinking about segments that are about the same as the curve that we start with for this exact net accumulation or exact total accumulation. But I could approximate accumulation by picking, like we did with Usain Bolt, 2 points that are close together, find the ratio of dy to dx between them, and state the rate for that interval. And then it changes from one interval to the next. But if you can maybe see what the problem is, we end up with a bunch of separate rate values as opposed to this, this step function here, as opposed to things that connect to one another. I can make them rate values that look kind of like a whole bunch of dots, but we're going to have to do something a little bit different than strictly reversing our process to get these dots or the short steps to connect to one another again. So we're going to have to make a modification to, it's not going to be precisely reversing our process. We're going to have to do something slightly different, but it'll be the same general idea, and we can end up with then an exact rate of change function that follows the pattern of where the very small steps or the dots would be by precisely following our same steps. So what we're going to be doing then is taking a look at some accumulation functions, a couple examples today, and then we're going to talk about more generally next week, Wednesday and Friday. Remember, we don't have class on Monday. Monday and Tuesday are fall break for ASU. It's the transition between online A and B session classes and a nice kind of break after midterms for you if you don't have any online classes. So don't show up to campus, it will be closed. But Wednesday, we'll catch back up and we'll continue where we leave off today. So exact accumulation functions, where we find them, they're all the sorts of things that we got as end result processes before. If I know a rate of change of something, I can tell what happens because of that change. So whether it's Usain Bolt running down the track, which probably wouldn't look like this, we saw what that looked like. You got farther from the starting line faster and faster, and this is maybe that, whatever that, I think it was a couple summers ago, that showed him like, it was like this, it looked like he looked to the side and took a selfie or something and then continued on. So this is like the, oh, slow down for a second and then go on your merry way. But I don't think he would end up winning races that way. But exact accumulation can be like anything. Anything can be thought of as an accumulation due to its components changing, the pieces of it changing in a certain way relative to one another. So even something as simple as like area of a square. You don't normally think of area of a square as an accumulation function, but if you can imagine, if I think of changing the side length, as the side length changes, the area changes by a certain amount. It's not just by the same amount as the side length changes. Those wouldn't even be in the same units. But as x, if I'm using x for the side length here, increases by a small amount, then the area increases by, well, it's related to this x squared. And depending on how small x is at the time, or how large x is at the time, the amount of change in area by adjusting x by maybe 0.1 inches or something. If I increase x by 0.1 inch, if x were a small number, that would increase the area more than if x, or less than if x were a large number. Sorry, I was saying my sentence halfway backward. Meaning, if you can imagine, let me just zoom this back. If x is 2, making that as close to 2 as I can, I know that the area is 4. If I change the area to 2.1, the area increases by, let's see, well, it changes from a 2 by 2 square to a 2.1 by 2.1 square, which is 4.41 square units. So it increased by 0.41 square units. If, on the other hand, the side length were already 4, and I change it from 4 to 4.1, the area is going to increase by more than the 0.41 square inches, if you can maybe imagine why. Thinking about taking I just added a thin strip of space to this area that goes all the way up this tall side and like this, and all the way over the top. It's 0.1 unit wide, and I added it all along. I'm going to have, let's see, 0.8 something extra square inches at this point. So increasing x by the same amount, small or otherwise, isn't going to increase my area by the same amount all the time. It depends on how large the area is to start with. So there's this weird relationship between the side length and the area, which isn't just necessarily fully explained by this, because I can talk about, well, what if I change the side length? How does the area change? And I can also talk about the rate of change, or that ratio of changes at different values of x. So it seems like a simple enough concept, area of a square, but it really kind of depends on what the current value of x is, how fast the area increases for these small changes in x. And so that's what we're going to be studying this chapter, how small changes in our independent variable, whatever it might be an independent variable for, in terms of a model of something accumulating due to it, small changes in that independent variable, and how the rate of change of that accumulation changes during that interval, or what the rate of change of the accumulation is during an extremely small moment. So regardless of what this rate of change function is, there is some relationship between changing the x and changing the area, changing the side length and changing the area. So without knowing what this rate of change function relationship is, I know one thing. I can express area as the accumulation due to mystery rate. I'll call it r sub f. So if r sub f is the function describing this rate of change of the area with respect to side length, then remember the meaning of this integral expression here. This measures all the accumulations in area due to this rate of change of the area with respect to side length. I got r sub f of t dt. So I'm going to let t take on all the values between 0. Now this would be a natural place for accumulation to start with a square, not negatives or not 3 or something. We could write it in terms of starting at 3. But starting from 0, when I have 0 area, I can measure all the accumulation due to that rate function afterward by doing this rate of change of the area with respect to side length times a small change in the side length. So this is our mdx expression with an unknown function serving the place of this m. But that's our goal for this chapter. Figure out what expression, what formula, what function rule do I need for r sub f of t, r sub f in general, in order to make this express area properly. Because if I know how to work from rate to accumulation, so I could estimate this, and we could estimate what sorts of rates are going to give us these accumulations, but that's not the order we did this in before. So let's take a look at this kind of the way we did the Usain Bolt problem instead. Starting at, notice this is not a graph of y equals x squared. Starting at a graph of y equals x squared, where the y, or the dependent variable then, would represent the area, and the independent variable represent the side length. So we'll do that in a second, but just we'll get back to this in a minute. Other sorts of geometry formulas, same thing. We'll be working with spheres as well. Just a quick thing, if I know the volume of a sphere is given by this formula, that's great. But that formula, just as with the square, if I modify the radius by a small amount, using x here for the radius of the sphere, if I modify x by a small amount when x is small, that just adds a small amount of, like, an extra candy shell to the outside of a small gumball. If I have a huge gumball and I increase the radius just a little bit, that's a candy shell that has to go all the way around the outside, so that's a little bit more volume, more candy required to cover something like this if it's large. And so we will be dealing with, we'll talk about the square and this sphere in specific, because they do have nice symmetric properties. But regardless, I know I could write that volume as a result of some accumulation function, it's called R sub f again, from, again, 0 to x. The volume in terms of radius x is the accumulation due to some mystery rate function we have yet to discover, but will on Wednesday, using accumulation between 0 and x, where we let this t vary between those. So just as a recap of things that we talked about before, any function that gives the exact amount of one quantity as a function of another is or can be conceived as an exact accumulation function. Could be net, could be total, depending on what we're doing. But one thing that we're going to talk about that's also easier about going this direction, whether I have net accumulation or total accumulation, whether I'm starting from a dependent value of 0 or something else, that doesn't affect the rates. The rates are the same regardless of that. If it's describing the same situation, the rate of change during whatever interval of independent variable values I'm talking about, the rates of change are going to be the same. It's just what's the overall value? That's independent of the rate. Just kind of like if I said I was driving between, I could drive the same speed on different stretches of road and have my rate be described as the same. It doesn't really matter where I started, if I started at home or if I started at school. If I'm driving at 50 miles an hour, it gets me the same distance. So if I have this distance, I can calculate the rate regardless of where it took place. So, as I said, this direction will be a little bit easier because there's not so much worry about what happened in the past. We just need to worry about the current moment one at a time when we're doing these. So the rate of change functions, finding those in any case, is our goal. So let's go back to the square, meaning if I'm thinking of the accumulation function, area is a function of side length squared. I'll call the side length x like we did before, and we'll just call this f of x here instead of a of x to be easier about it. But again, this is not a graph of a parabola, but we can, or this y equals x squared, but this is what we're measuring the changes in, geometrically speaking. If I want to think about the graph that compares these correspondence points, the side lengths and the areas, that would look like this, not like a square. So I can't measure the changes geometrically by measuring length and width from this, but I know that each point in this curve, this is an accumulation function. Now, we have to kind of change gears. We've gone back and forth a few different times between looking at graphs of an amount of something or an accumulation of something versus graphs of rates of change. Make sure whenever you approach a graph, orient yourself to it first, look at it, make sure you understand what the quantities are that are being compared. So this is side length along the bottom, x, and our area in square units along the vertical axis as the dependent variable. So I'm sure that you agree with me, this is the graph of dependent variable equals x squared, independent variable squared. So let's take a look at how we would piece together an approximate accumulation function. Kind of showed an outline of what we want to do with this. But if this is an exact accumulation function, and I want to make an approximate accumulation function, something that has constant rates of change at various moments. So what would it look like in an accumulation function? This is exact. This doesn't have constant rates anywhere. I could zoom in super close and see approximately constant rates, but what do constant rates of change look like if I'm looking at the accumulation function? what would I need to see in order to like zoom in close enough to know I have an approximately constant rate in a moment? Straight lines? Straight lines how? Like that? Yeah, no, I wouldn't. Yeah, this is if this were a rate function, constant rate of change, I'd be like, all right, so I'm going to pretend I've got one rate for a little bit, and what? But this isn't what I want. Because this would be the area is nothing for a while, and then the area is a quarter for a while or something, and then the area is 1 for a while. So there's during each of these intervals, which are on this 1/2 of a unit long, there's no accumulation of area. The only accumulation happens when we decide to change value. So that's not quite how we want to set this up. But we do want to have straight lines. But straight lines how? Like think about what you did on the Usain Bolt graph when you're looking at how far he was from the start. You zoomed in, we pick a couple of points, and we compare dy and dx. So what I need is not this. This is what I do to a rate function. Constant rates look like horizontal lines. Constant rates in a rate function look like horizontal lines, same rate value. If I want a constant rate in an accumulation, that's a linear function of some sort. It doesn't have to be horizontal lines. If nothing is accumulating, it would be. But I've got something accumulating. How about instead of those, if we take points every so often and kind of play connect the dots? So I could imagine maybe piecewise linear, like the chunky approximate accumulation function that we had as our kind of skip over step after we got past it. We're like, oh, they really don't like this. That's the thing that comes from the summation. But if I connect dots, oops, let me scoot this a little bit. Maybe. Come on, let me move this. There we go. If I connect dots, draw the line segments with both endpoints on the curve. Like maybe you don't have to do it that way, you could do it other ways, but like if I put a dot at the origin here and then one maybe half a unit later, if thinking about the half unit, or a unit later, and then draw a straight line between them. A straight line in an accumulation graph of any angle represents a constant rate of accumulation, but I don't want constant rates of accumulation 0 throughout like those horizontal lines. Those aren't very good approximations. I want my accumulation to build. So if you can imagine, click, there we go, connecting the dots every so often. And so here, let me put some points on here so it's easier to see. But here's a dot that I just placed at the origin. Here's one at 1, 1. There's another one here at 2, 4. If we use those, now these are fairly poor approximations to the curve, but what we're trying to do is approximate what's going on with this accumulation, but by generating a different accumulation graph that shows constant rates of change that are similar to, if possible, our exact rate of change. So meaning between 0, 0 and 1, 1, those two correspondence points are ordered pairs. The red curve obviously changes. It moves at a slow rate upward and then a faster rate upward, meaning at first area accumulates slowly and then more quickly as the side length increases from 0 to 1. This blue line accomplishes the same amount. It gets from 0, 0 to 1, 1, but using one rate all the time, using a constant rate to get from that starting value to the ending result within that, it's not a time frame, but within that amount of side length change. So what would be the rate, the dy over dx, or m, for this first interval here? Well, between 0, 0 and 1, 1 on this blue line, that looks like a change in the vertical dy value of 1 and a dx value also of 1. They're not on the same scale, these axes, but this is 1 to 1. So that would be my m, of m dx. So I've got a constant rate of change demonstrated by that first blue line segment. That's a slope of a rate of change of y with respect to x of 1. And in the second interval here, again, not particularly close approximations, but here's our coordinate points. We can calculate the ratio of dy to dx. dy is 3 and dx is 1. So this is a 3 to 1 ratio. So there's our m. dy dx is 3, dy over dx. So using a rate, if you can imagine what we did last chapter, if I said, here's a piecewise rate function, an approximate rate, it's 1 if x is between 0 and 1. I'm just going to use interval notation here, 0 through 1, because I don't have quite enough space, if x is in that interval. And it's 3 if x is in the next interval. Oops. No, yeah, I was right. 1 through 2. And then if I were to continue, I'd pick a new rate between 2 and 3 and so forth. So if you can kind of see, oh yeah, if I had a piecewise rate function, first I use a rate of 1 and then I use a rate of 3. Over the first unit, I would accumulate 1 square inch of area. And over the next unit, I'd accumulate 3 times 1, 3 square units of area. So by the time I got here, I would have accumulated a net amount of 1 plus 3, 4 square units of area. Now, it accumulates the same amount, just not in the same way, so that things in between those points wouldn't be precisely accurate. If I want to know what's the area according to this rate function, if I have x equals 1.5, I'm not going to get 2.25, I'm going to get something else. So just as a setup though, I don't want to go through using these rates to generate accumulation like we did on the last test, but just as a setup, if we can imagine making an approximate accumulation function by picking some points on the curve and drawing line segments between them. Pick an interval width. This was just picking an interval width of delta x equals 1. And then generating the constant rate of change over that interval that would accumulate the same amount by comparing the ratio or comparing the values of dy and dx over that interval. I can get rates that accomplish what happens in the interval just at a constant rate as opposed to at the actually varying rates that there were. So we have constant rates of change, but we'd like to have better constant rates of change, so how would we make better approximations? What's our trick for making a better approximation than what we just did? Yeah? Yeah, make the distance between the points smaller. Shrink down our how often do you pick a point and connect the dots. Shrink down our intervals, our dx's or delta x's. So delta x we decided was the preset length of evenly spaced intervals. So let's say that we have delta x equals a half instead of 1. I don't even know if you can see from where you are right now. I'm just going to cover that up. Doesn't say anything new. But there's a blue and a red graph here both. They're kind of right on top of one another. This is just using 1/2 as that delta x, the distance between points, and already it looks very close. So this is a very good approximation, just using 1/2 as the interval length between these points. And we could compute all those different coordinate pairs and the slopes between them, but it would still be a piecewise rate function, this time with 4 different rates, using a rate between 0 and 1/2, 1/2 and 1, 1 to 1.5, 1.5 to 2, just to go the same distance as before. But regardless of whether I work these out or not, this r of x, this approximate rate function, that is what I'm trying to write, is a piecewise function. I have 1, 2, 3, 4 different parts. One between 0 and 1/2, one between 1/2 and 1, and so forth. So our goal is to write a rate function that isn't just a sequence of a whole bunch of different dots. So I get a really good sense of what the values, I'll put 3/2 here, what the values of the rate function are going to be, but by just writing a series of distinct points, and that's supposed to be 3/2 here, 3/2 or 1.5, this is never going to suddenly turn into like 4x plus 9 or some sort of formula. It's always going to be just a series of dots or different values that I use for small amounts of time, but it looks like dots from a distance. So there's techniques you could use. You could use a linear regression or some sort of regression on a calculator, put in your data points, see if you can find a curve that goes through it and come up with a formula that way. But that sounds kind of counterproductive because the calculator's doing the stuff that we're supposed to be able to do. So we need to be able to take a rate function like that, because we don't actually need to write out the approximate accumulation. Our goal is to write the rate function. So notice I'm not worried about, oh, how do I write the formula for this blue line here? All I want is its steepness, its rate of change. And all I want for this section is the rate of change. So I don't have to go through and find, luckily, those horrible piecewise accumulation functions where you need the y initial plus m dx. All we need is the m. So we're stealing just little bits and pieces out of the information that we have available, which is nice. That's why, as I said, this direction is going to be a faster process than going the other direction, because we don't need to think about quite as many details as last time. We're kind of getting rid of some of the details and just looking at the rate of change. So, all right. In any case, if we wanted to, is this going to click for me? There we go. If we wanted to, we could find the constant rate of change for these smaller intervals, but like I said, it'd just be a sequence of, in this case, 4 numbers as opposed to 2. And we could write an accumulation function, but let's not, because we don't actually need that. If we wrote the whole thing, we could go through and take 15 minutes and write the whole accumulation function, the piecewise linear function for all the equations, the function rules that represent each of these segments of this blue line. But then the next step would be, and what is the steepness? What is the slope? What is the rate of change of each of those sections? Which would be, oh, take out all the hard work you did and just put the rate in there. So rather than writing out the whole accumulation function, we'll just focus on the part that we actually need. We'll skip ahead and think about how would I do this in general? So I'm going to use the picture that we had before, but we're going to think of this not necessarily as being a of x equals x squared, and these are the values at like 0, 0, 1, 1, and 2, 4. Just think of this as some general graph where we use this process. If this red curve here, generally, let's just call it f, as opposed to like f of x equals x squared being demonstrated here, or y equals x squared, the graph being shown. That's our exact accumulation, general function f. The blue graph A here, if f is exact accumulation, this piecewise linear function, that's our, instead of exact accumulation, is going to be approximate. And you can call it net or total. Based on our previous example, that was area of a square, so that'd be total. It started from 0, and that's the smallest we could have ever started from. But it would be approximate in any case. And so for every x value, not just for talking about intervals at a time, we need to be able to describe, in general, what's the constant rate that I would use. So we're going to use some of our notation from earlier chapters, from chapter 5, to describe in general, well, let's say that x is here. So if x is here, I don't know necessarily which interval that is. Is this the 17th interval? Is it the second interval? Is it whatever? That's not important in this case because I actually don't need to know all the completed intervals and the current y value, and that all I need to do is calculate the rate. So it doesn't matter what interval x is in. All I need to know is how do I describe what the rate is for the interval that it's in. So just picture-wise, it looks like it's in this interval that goes from that green dot to this green dot. Now, if this x value right here is at the left end of the interval that x is currently in, what's the name of this x value here? Using terminology from last chapter. If this x value is at the left end of the interval that x is currently in, left of x. All right, so here's a mystery value, left of x. If this was our if this was our, actually just our parabola, this would be, looks like x equals 1. And then x is slightly bigger than that because it's in that second interval when we had the poor approximation. But just imagining any general curve f here, displayed in Cartesian coordinates, that x value at the beginning of the interval that x is currently in is called left of x. What about the x value at the end of that interval? If our interval width is, let's say, delta x units wide. If this is delta x units wide, how could I describe this location? Not right of x. What could I, if it's left of x is here, and then I want to jump delta x to the right, left of x plus delta x, right? So left of x plus delta x. So the interval that x is currently in, and that's the only one we're ever concerned about at a time to find a rate, it only requires knowing about the interval that x is currently in, would go from left of x to left of x plus delta x, which mean I could also describe the vertical coordinates, the dependent variable coordinates, this height here, which happens to be smaller in this case but doesn't need to be smaller in general. If this red function is called f, and our blue curve and our blue straight lines and our red function meet there, it's the same point. This dependent variable value would be f of left of x, right? So f of left of x is the y value that corresponds to left of x on the f curve. It's also a of left of x, but I don't really want to have to write out function a, so I'll just refer to f, the easier one that was already given. So same thing here, the y value that corresponds to this second point at the end of the interval. That height would be f of, well, the x value there. F of left of x plus delta x. Left of x plus delta x. So for any x within this interval, and this isn't a special interval, this is a general interval for a general function f, just any x we want. I just used the same picture from previously. None of these are only pertaining to parabolas and squares, square areas. So I could find an expression for this steepness between those two green dots, the ratio of dy to dx. So my dy value I can measure here. My dx value I can measure there. Now I've used the whole interval, so it's the dx is delta x in this case. But this ratio dy to dx would just be a lovely subtraction problem, right? The difference between these two over the difference between those two. Oh, well, the denominator is going to be easy. The difference between the left and right end of this interval for x is just delta x, right? So this is going to be a big mess over delta x. But all that is just this expression and that expression. We want final minus initial subtracted. And in this case, the final one in the picture appears to be larger. If it was smaller, we just have a negative result. That's fine. But we want final minus initial to represent change. And if we have a decrease, we want that change to come out as negative. In this case, we have an increase. So let me clear off some of this so I have some space to write. There we go. But this approximate rate function r should be this ratio here, which the mess in the numerator is just final y value at the end of the interval, minus the y value at the start of the interval. So delta y and delta x, there we go. Yep. I wrote some of this down typed-wise, so I'll bring it up and clear my handwriting. There we go. So we've got left of x and f of left of x. Left of x plus delta x and f of that. So writing out that mess in the numerator, as I said, is just f of left of x plus delta x minus f of left of x. And again, you can't do the subtraction here. The things that are subtracted are function values. I don't know what function f is. You can't like cross out the lefts or anything. This is just f of the end of an interval minus f of the beginning of the interval's independent variable values, all over the difference in those independent variable values. So here's an expression that gives us in general for any curve f and any interval width delta x, an expression that gives the rate of change as a constant that applies to a value x within that interval. So, like I said, this isn't going to be quite what we need to use, because if you can imagine what would happen if I were to graph this rate function as x moves from, I'm just going to use 0 to 1. As x moves from 0 to 1, I'd have one constant rate the whole time, and then suddenly it would jump. And then suddenly it would jump again. I'd get that piecewise rate function. But this, as one line, defines an entire piecewise r of x. Like I was writing out for particular values last time with like the value from the first, second, third, and fourth interval would be like, what, a quarter, and whatever those subtractions give you. You can define the whole rate function without using a piecewise definition this way. And we could write the approximation function, but as I said, we don't need it. We don't need to write the whole approximate accumulation function in order to write the approximate rate function. We can kind of imagine it being there and then skip past actually writing its formula, because all we need is just the rate portion of that formula. So we're lucky in this case. We don't have to write all of that. We're not going to have an equivalent write this horrible accumulation sum. We'll just jump straight to this r of x equals, and then we have this one-line expression. We can write it without using a piecewise expression, because for any current value of x, this same exact function applies. We have this function left of x that we designed in order to express the left end of the current interval that x is in, or the left end of the interval that x is currently in. And we don't need the previous interval's information at all to calculate rate. All we need is the current interval's beginning and ending positions. So if I wanted to write out the accumulation sum in general for this, I could do a kind of fancy trick here. Say, okay, well, my accumulation y initial plus mdx, that's what this is here. So I could write this. This is not particularly usable, but this is y initial at the beginning of the interval that x is currently in. This is my initial y value. The rate for the interval that x is currently in is this r of x, just that messy expression from up there. And then dx, for any x within the interval, dx, how far x is into the interval, is this x minus left of x. Same as it showed up before, but nicely, we can write this all in one line. So if I wanted to write this accumulation, I don't have to write it as a sum, but notice this f of left of x. It's, well, you'd have to know a lot about the accumulation in the first place. These are not easy to evaluate. This expression here, though, is really what we're going to be working with. So I could write out this accumulation not as a piecewise function, but as a single line sort of expression. It changes a chunk at a time. This f of left of x is our interval, and then as x goes through this interval, this dx grows, and r of x stays constant. So I use one rate for a while until I jump into a new interval, at which point left of x changes meanings, r of x changes values, and x minus left of x starts again from 0 and grows. So this would generate the approximate accumulation we want, but we're not really going to focus on writing that out, so don't worry about having to do that. It's not long, but it's just, this is an abbreviated form of what actually would describe these blue straight lines here. So our goal then over the next, is this going? Our goal then over the next few weeks is going to be to develop this general process of how do I get better than this estimate, better than this approximate rate of change function r of x, how do I make it more exact, and how do I actually make it into a continuous function instead of this piecewise step function that we would have from evaluating this at various values of x. Because this doesn't look like it, but it's a step function. It changes values suddenly it has one value for a while when x is within each individual interval. This numerator remains the same, and the denominator is always delta x. The second x jumps into the next interval, passes another dividing point, left of x changes meaning, so these two change, and it keeps the same value for a while, for a however small a moment you want, but it's a constant rate, and this just has a series of different numerical values for any f. So what I want to do is make a continuous function, something where it blends from one value into the next. And our method of doing that is going to be to alter our approach a little bit here, but that's what we're going to talk about after break, not today. We're going to compare this method that is more precisely backing up from what we just did to a slight variation on that that'll help us get a continuous function, something with all the values connected, where r smoothly blends all the time from one value into a next, if it's possible to smoothly blend. As we know, rate of change functions don't always exist at a moment. Sometimes there are going to be jumps and skips and whatever. But if I can get something that at least isn't just a series of individual numbers, that would be great. So that's what we're going to work on next week. Have a great weekend. Enjoy your extra time off if you get any, or your extra time at work if that's what you get. But take a little bit of a brain break. There's no Canvas quiz that's going to be due. I'll just assign you some reading.